electrochemistry today. So the topic of advanced electrochemical calculations shall be dragged through to completion. So I would like to state that the concept of electrochemical equations is rooted in the fact that cations, rooted in the idea and principle of electrolysis. Electrolysis is a very common technique. It's a very common technique, and it's been used to extract, purify, refine, and plate metals. So it's the idea of advanced electrochemical calculations comes from and is rooted in the idea and principle of electrolysis that is used to extract, purify, refine metals of all sorts. It works best with metals of group D, transition metals, group 1, 2, and yeah, that's about it, because when you go from group 1 to, so when you move over to 3, 4, 5, it becomes very, very difficult. So electrolysis is useful. So that's the industrial usage of it. Now, it is not to say that it can't occur for non-metals. Obviously, anions also get extracted onto the anode. So in electrolysis, you've got a container containing the molten or the aqueous. Molten or the aqueous. Molten or aqueous, pool containing the desired metal. Now, when you stick two metal plates and then you connect them across a circuit, and you've got a voltmeter, and you could add forward bias diode, and you could add a resistor, and you could do all sorts of to make it and you could add electronic components as well to make it quite sophisticated. But the idea would be that one of these plates will be a cathode, and one of them will be an anode. So one of them will be a cathode where cations, like metallic ions, aggregate, and where an anode will be where anions acquire their metallic or non-metallic form. So cations will come back to their metallic form, and anions will come back to their non-metallic form. So by the principle of oil rig, the cations will be reduced. So cations, because cations, they ionize after having lost the electrons, so they undergo oxidation. When they come back to the cathode, they are reduced into their natural metallic form. So cathode reduces. So cathode reduces, but is oxidized in the process. Anode does the exact opposite. So anode oxidizes, but is reduced in the process. It's reduced in the process. So now you can see cathode cations, anions, oil. The principle of oil rig dictates that cations will be reduced at the cathode, and anions will be they'll be oxidized, but they'll end up reducing the anode in the process. So I hope you understand. I hope you appreciate where the whole principle of electrolysis is rooted in. Now, if you were doing electrolysis of silver chloride in aqueous form, aqueous solution, AgCl plus H2O, and it was Ag aqueous, liquid, aqueous. So, and then it was Cl plus H plus OH, all of them are aqueous. Right. So you would then try to, so silver would go to the cathode and chlorine gas would go to the anode. Now, when silver goes to the cathode, when 1 mole of silver is deposited onto cathode, the mass of cathode goes up by 108 grams. Yes, and so that would become heavy, and 1 mole of electrons would have been absorbed by silver metal. So now you can grasp the philosophy of calculational analysis rooted in electrolysis. So the principle of electrolysis is to extract, purify, refine, and plate metals, especially group D, group 1, and group 2. Cathode, so you set up an apparatus, something that looks something like this. You've got a container that can't be affected by high temperature changes, and then you have a molten or an aqueous solution pool of the required metal and non-metals. You stick 2 plates of different materials, sometimes it's carbon, sometimes graphite, sometimes it's platinum, and then you accumulate the cation metal onto the cathode, and non-metallic gases or debris are accumulated at the anode. Now, by the principle of oil rig, cathode will reduce the incoming cations, but will be oxidized in the process. And anode will be oxidizing the incoming anionic atoms, but will be reduced in the process. So I gave you an example of the electrolysis of silver chloride. If it were then 1 mole of silver when 1 mole of silver is deposited onto cathode, the mass of cathode goes up by 108 grams, and it would have absorbed 1 mole of electrons by during that process. So the first equation in electrolysis that the students need to be mindful of is something they've come across in physics as well, is Q equals IT. That's charge in coulombs, current times time. That will be useful, but then there's another one called Q equals mole of electrons times the Faraday number of mole of electrons. That'll be, no, hang on, that would be the second one would be mass deposited equals current supplied times time taken for that current to be supplied divided by the Faraday constant, which is 965 coulombs per mole, and times the atomic mass of the deposited divided by the charge, the valency. So that's also another one you need to understand. So the first one was that, the second one is this, and then for the Faraday constant would be, and then you'd have to, for Faraday, then another one you need to be mindful of. And then another one you need to be mindful of is Q equals N, number of moles of electrons, times the Faraday constant. So that'll be, if we simplify the equation, that'll be IT equals number of moles of electrons times the Faraday constant, which is 96,500 coulombs per mole. Yes, so that's what you have to understand. Now you've got the first equation, which is very, very simple. Second equation, and then the third equation. So Ne, so the capital F or the uppercase F here would mean Faraday's constant. So Q equals IT, and then mass deposited is Q over F times AR, the atomic mass, over the valency. So, and then you'll have to, for gases, it'll be volume of gas released equals current times time divided by the Faraday constant times 12 divided by Z. So Z here would be the charge, the valency, oxidation number. That'll be the oxidation number. So you'll have to, now when you write it simply, it'll be Q over F times 12 over Z. That's how you write it. So IT over F times 12 over oxidation number. That's for gases, volume of the gases released. And then you'll have to adopt another simplicity of Faraday's constant, which will be, you'll have to understand that Faraday constant will be always Q over coulombs per mole. So it'll be 96,500 coulombs per mole. That's how it'll always be. So coulombs per mole. Coulombs is charge, and that's that. And so now we'll get on with the calculations. The calculation I want you to understand is silver again. So silver, 1 mole of silver will accept 1 mole of electron to become 1 mole of deposited silver onto the cathode. So 1 mole of silver would accept 1 mole of electrons to become 1 mole of solid silver. And this is what you need to understand, that when electrolytes conduct an electric current, chemical changes take place at electrodes, oxidation, reduction, current, charge, voltage. So the electrode reaction depends on the nature of the electrolyte and the material of the electrode, like platinum or graphite or gold or copper. I mean, at the cathode, the electrode reaction involves gaining electrons from cations, and it's the opposite at the anode. So electrolysis, in the industry, electrolysis is done on molten salts, aqueous salts, and it's done on it's also done on I think acids and alkalis as well. Yeah, acids and alkalis. So if I were to ask you, what is the cathode reaction when molten lead to bromide is electrolyzed using the carbon electrodes that are very inert? How many moles of electrons are gained by lead ions to give 1 mole of lead? So lead bromide, we know that lead is 2 positive in this case, and bromide is 1 negative. So the valencies will cross multiply. We'll get PbBr2. When we ionize it in a molten form, it would be so that's what it would look like. And so now if we bring it outside, we'll see that lead, in order to assume back the metallic form, it'll have to take 2 moles of electrons to become metallic lead. And so now we'll have to do that. That's how things are for now. So the first example I'd like to take you through is of sodium. So sodium would take 1 mole of electron to become 1 mole of metal deposited at the cathode, followed by copper would take 2 moles of electrons to become an inert solid, and then nickel would take 2 moles of electrons as well to become 1 mole of solid at the cathode. Now you can see the relationship of the number of moles with the oxidation number. Number of moles with the oxidation number. So you can see, higher the oxidation number, higher the number of moles of electrons required to bring it back into its metallic form. So if it's 1 positive, it'll need 1 mole of electrons. 2 positive, it'll need 2 moles of electrons, and 2 positive. So, and then if we come on to a trivalent atom, just for the change, it'll require 3 moles of electrons to become a solid. And similarly with aluminium, it would require 3 moles of electrons for it to assume the metallic form. And if we came across a tetravalent, that then obviously would require 4 moles of electrons. Now by equimolar ratio proportionation, if we have sodium ions here, and we know that 1 mole of sodium ion requires 1 mole of electrons to assume metallic form. So how many moles of electrons would 0.2 mole of electron, 0.2 mole of sodium take? it would be, because there's a unimolar ratio, equimolar, both are equimolar, so it would 0.2 moles of electron, 0.2 moles of sodium ions would require 0.2 moles of electrons to reach a state of atomic purity, and 0.2 moles by Avogadro number of particles would be moles times the Avogadro constant. So that would be 0.2 times 6.02 times 10 to the power 23. So that's how many electrons would be required for this many particles, this many atoms of sodium to reach 0.2 moles of atomic sodium, and that would be, and the mass would be so 0.2 times 23, so that would be 23 divided by 5, round about 5ish, 4.7 something, around about 4.7 grams of sodium shall be deposited onto the cathode when 0.2 moles of sodium ions require 0.2 moles of electrons to be deposited onto the cathode. So around about 4.7. I don't have my calculator with me at the moment. Now, if we do this, now for copper, we'll do another example. For copper, it'll be, because copper requires 2 electrons to reach the atomic state. If 0.25 moles of copper is available, it would require 0.5 moles of electrons, half a mole of electrons, because there's a 1:2 ratio. So for every 1 ion of copper, 2 moles of electrons are required to facilitate it reaching its atomic state. So it'll be 1:2, 1:2, 1:2, and then if we had nickel that is also divalent and requires 2 moles of electrons. So if you had half a mole of nickel, which is quite a lot, and then we would require 1 mole of electrons, exactly Avogadro number of electrons, 6.02 times 10 to the power 23 electrons, to satisfy it into a nascent metallic state. So you can see the ratio is 1:2 here. So for every 1 mole of nickel, 2 moles of electrons are required. And then the same, for iron 2, it would be the same. If we had about 0.2 of iron atoms, we would not 0.2 moles of iron atoms, we would require 0.4 moles of electrons. Yes, but if we had 0.2 moles of iron 3, it would be 0.6, because there's a 1:6 ratio. There's a 1:3 ratio, sorry. So there's a 1:3 ratio, so it'll be 0.2 times 3 equals 0.6. So this is how you're able to deduce and infer how many moles of electrons shall be required for 1 mole of a trivalent or a divalent or a monovalent atom with certain amount of mole, 0.2, 0.2, 0.5, 0.1 and stuff. So if there's a 0.1 of iron 2, it would require 0.2 moles of electrons, and if there's 0.2 of iron 3, it would require 0.6 moles of electrons for satisfaction. So that's that. And how many moles of, and as I explained, So what would happen is this would be 0.2, this would be 0.6, but this would be 0.2 because the ratio is equimolar here. So 131, 131. And this would be 0.2 as well. This would be 0.5, half a mole of nickel, a fifth mole of iron, a fifth mole of iron, so iron 2, a fifth mole of iron 3, even though the electron, the volume of electron is just like the volume, sorry, the moles of electrons are increasing, fluctuating, going up and down, even though, but the ratio of the metal will always be to its metal. So 0.2 mole of iron will yield ions would yield 0.2 moles of iron metal. So half a mole of nickel, half a mole of nickel, half a mole of a fifth of iron 3 would be a fifth of iron 3 metal. So here in this case, a quarter mole of copper would yield a quarter mole of copper. So even though you've got like varying numbers of moles of electrons, the molar ratio for the metal to its ions would remain the same. And now we're going to start calculating mass deposition. And mass deposition would be so this is the current, that's the time, that's the Faraday constant, 96,500 coulombs per mole. This is the atomic mass, and that's the oxidation number. So now we'll be calculating mass. Start calculating. The first question I'm going to do is how many moles of electrons are needed to change 1 mole of hydrogen ions to 1 mole of hydrogen molecules. So hydrogen is a cation, and it would be released at a cathode, and so it'll be 1 mole of electron for hydrogen, nascent hydrogen, but then that hydrogen will have to move to another hydrogen to become H2. Now the equation will be presented as 2H plus 2 moles of electrons leading to H2. That's how the equation will be presented, and it would be presented with the symbol gas. So that's how it would be. So rather than writing this and this, you write this the first time. And for oxygen, it would be 2O2, release of 4 moles of electrons with 1 molecule of oxygen, and there we go, eureka, you've got your oxygen being released at the anode. For chlorine, it'll be at the anode, and off you go with chlorine at anode. Similarly for bromine, and it would be for every 2 moles of because it's monovalent, it would be releasing 2 moles. And for gases that are divalent, I can't think of any other. So oxygen, and I think the other one would be, let me pull out my periodic table. Here's the periodic table. So we can see we've got fluorine, chlorine, bromine, and that would be releasing the same way. And then we've got oxygen. I don't think we have any other divalent gases. So I'll leave it at that. So now divalent gases will be requiring 4 moles of electrons to be released. Hydrogen would require 2 moles of electrons to be released, and chlorine would give off, and chlorine, bromine, fluorine would give off 2 moles of electrons each at the anode to be released onto the anode. And you can then collect it from there onwards or just let it release itself. Now you have to bear in mind for electrolysis, not all ionic complexes or ionic composites are released or disintegrated. So complexes like sulfate, carbonate, phosphate, and also chloride, and you have some other metallic complexes as well that will not be released. So that's called the preferential discharge, where oxygen, where OH, O2 minus, and so nitrate is also one of them that will not be released. So in electrolysis, these sulfate, carbonate, phosphate, chlorate, nitrate, and other tough complexes like these will not be released, whereas soft complexes such as hydroxyl, oxygen, chloride, chlorine, fluorine, bromine, iodine, and they will be released, but nitrates, chlorates, phosphates, carbonates, and sulfates will not release itself. They will not be disintegrated by the electric current because, I mean, it's quite evident that their internal electrostatic bonding forces are stronger and cannot be overcome by the Coulombic discharge, the Coulombic disintegration produced or induced by the circuit. So the circuit's Coulombic forces are not strong enough to break the electrostatic or the covalent interactions of these complexes: sulfate, carbonate, phosphate, chlorate, or nitrates. But these ones are weak enough, and they will be discharged at the anode or cathode or wherever they be. So these will be and they will then be released as gases. So we have to realize and appreciate that not every ionic, anionic, cationic complex will disintegrate and discharge. Some of them won't. Now we've established the relationship of moles of element, moles of iron, moles of electrons in the sense of an equation. So we've now gained an understanding of all of these components in the sense of an equation. So, we've realized and understood that it's different. The number of moles of electrons will fluctuate for monovalent, divalent, and tri and tetra and pentavalent ions. And they'll also vary for larger complexes as well. So the number of electrons released by a larger anion or absorbed by a larger cation will be different to a simple single monovalent, divalent, trivalent, tetravalent anion or cation. But some materials are inert. They do not get affected by electric current, and that's why they're used as electrodes. So the first one is graphite. Well, graphite does dissolve in aluminium electrolysis, but I'll get to that later. Then you've got platinum. Platinum's the top choice. Then you've got gold. Gold isn't used very much because a lot of it would be required to build up an electrode. And then you have carbon and gold, platinum, graphite. These are very popular electrodes that are used in the dissociative electrolysis of different ores, molten ores, aqueous, salts, and what have you. So that's that. And now from here onwards, we'll move on to the quantization. The next topic we're going to do is the quantization of electrolytic dissociation. So that's that, and we'll move on to the first one, that is Q equals IT. So if in a circuit I'm passing, or I choose to pass 0.25 amps of electric current for 2 minutes, how much electric charge would I have accumulated when a quarter of amps is being passed through a circuit for 2 minutes? So it'll be Q equals IT, and it'll be 0.25 amps times 2 times 60. So that'll be 0.25 amps times 120 seconds, and that'll be 30, so 30 coulombs, quite large amount of charge. And so what would you do if how much electric charge is used when you're doing when you're passing the current? I'll make a table here. When you're doing it for 0.2 amps of current is passed for 600 seconds. 0.5 amps is passed for 20 minutes. And 1 amp is passed for 1 hour. So how much? What would happen? So for the first one, it'll be 120 coulombs. For this one, it'll be 20 minutes. 20 minutes times 60 times 0.5. That'll be 600 coulombs. So 0.5 times 20 times 60. And then for this one, it'll be 3600. So that'll be 3600 coulombs. So I hope you understand. Sorry, yeah, so that's the table. By using Q equals IT, we multiply I, the product of, so Q is the product of I and T, and for the first one we'll get 120 coulombs, and for the second one 600 coulombs, and for this one 3600 coulombs, because 1 hour in actuality is 3600 seconds. So you multiply 3600 by 1, you get 3600 coulomb, and then 20 times 60 is 1200 times half would be 600 coulombs. So I hope we were able to establish the relationship Q equals IT in terms of electrolytic substitution of current in a circuit. So now the next equation we'll be practicing is, it's going to be Q equals NE, Q equals NF. NF. Now we could also use IT equals NF. We can use that, and we will in future. So when we've got the current and the time and we know the Faraday constant, but we don't know how many moles were passed, we will be using this. But for now, we'll stick to this, the top one. So we'll stick to the top one, that is, and then we'll now calculate the amount of the moles of electrons, and that'll be, so if the current supplied is 0.4 amps for about 1930 seconds, then how many moles of electrons have been flown through? If 0.4 amps has been passed for 1930 seconds, and how many moles of electrons have been flown through? So that'll be, the answer would be Q equals, you always have to write the equation even though you may remember it, so it'll be IT divided by F equals N. So we'll have to do, I'll take it here slightly here because of space, so it'll be 0.4 amps times 1930 seconds, it'll be 8 millimoles of electrons. That in Avogadro's number would be round about 4.8 times 10 to the power 21 electrons. So around about 4.8 or 5 billion, I think billion, thousand billion electrons. So quite a lot of electrons would have circulated through the circuit. So similarly, you'll have to come across questions, how much electric charge. So now we will twist the equation and we'll say how much electric charge is carried by 0.2 moles of electrons. So that'll be 0.2 times 96 coulombs per mole. Always write the units, and that'll be 19,300 coulombs. We could do the same for 0.004 times the answer would be 386 coulombs for 0.005 moles of electrons. 0.05 moles of electrons, it would be 4,825 coulombs. So that's another way of looking at the equation. And so how many moles of electrons are needed to carry the following amounts of electric charge? 1930 coulombs, 482.5 coulombs, 96.5 coulombs, 28,950 coulombs. So now we are twisting the equation into finding, so first we found out the electric charge for these moles of electrons, this, and this. Now we'll be twisting the equation so we've got the charge. Now we want to find out the moles of electrons. So it'll be N equals Q divided by F. and then you'll be putting 1930 and 482.5 and 96.5 or 28,950 coulombs on top, dividing it every single time by the Faraday constant, which is 96,500 coulombs per mole, and you'll get the answer in mole. I'll do the first one for you. So I'll take 96.5 coulombs divided by 96,500 coulombs per mole. So the coulomb cancels, mole goes on top, and that'll be 1 millimole of electrons. So that's that, and so this is how you'll take 1930 divided by 96,500 and then 482.5. So whatever charge you have, you divide it by the Faraday constant to get the number of moles. And however many moles you've got, you'd multiply it by the Faraday constant to get the charge circulated in the circuit. So that's how this equation is related. Q equals NF, and then you can rearrange it to find the number of moles. So this equation is quite key and will be ever so useful. Now, I want you to focus on this question. Example 6H. The example 6H says, in the electrolysis of molten lead, what mass of lead is formed at the cathode and when a current of 1 amp and is passed for 965 seconds. So it's trying to simplify it for you. So first we'll find the charge. That'll be Q equals IT. And we get 965 coulombs. Then to get the number of moles transferred, we divide it by the Faraday constant, so we get 0.01 mole. And then we use the equation where we see that the equation ratio is 1 to 1, 1 to 1, 1 to 1. So 0.01 moles of electrons must have been given to half the mole of lead, so half of whatever the mole of electrons were, because of the ratio 1 to 1. So it would have been 0.005 moles of lead, and then given the relative atomic mass of lead, we multiply the relative atomic mass of lead to the number of moles of lead that accepted 0.01 moles of electrons, and it gives us 1.035 grams of lead. So here you started off from Q equals IT, then you used Q equals NF, and then you used equimolar ratio proportionation to find out, and then used mass equals moles times AR, atomic mass, to calculate the final mass deposited. There are simple formulae that you could have used. You could have just done that, and that would also lead you to the same conclusion, I suppose. Let me try this equation. And if you did 965 coulomb divided by 96500 times 207 divided by 2, yeah, it would still lead you to the same mass. So it would also give you the same mass. So you multiply the current, that's 1 amp times times 965 seconds, you get 965 coulomb divided by 96500 Faraday constant, you get 0.01. You multiply it by 207, and then you divide it by 2, which is the valency or the oxidation number of lead. You get the same answer, which is 1.035. So this formula is correct, it's verified, and it is indeed ever so useful, and it can allow you to skip a lot of steps. So this example is quite simplistic, but if we were to do it in future, we'd be using this formula, because it's ever so useful. IT over Faraday constant times atomic mass of the required or metal under discussion divided by the oxidation number of the element under discussion. So the other example I'd like to take is when molten magnesium chloride is electrolyzed It uses a current of 0.8 amps for 965 seconds. Again, it is trying to simplify things for you. And 0.096 grams of magnesium is formed. So what's the charge on magnesium ions? So I'd use the same equation. So I'd get M mass equals Q charge over Faraday constant times atomic mass of magnesium divided by the oxidation number. So I'd rearrange it for the oxidation number, and that'll be Z equals MF divided by Q and the AR. So I would do 0.096 grams times 96,500 coulombs per mole divided by IT, which is 0.8 amps times time 965 seconds times 24 grams per mole. Always write the units because the units will cancel out to give you the correct. So the oxidation number will be so it'll be half. I think the equation got flipped. So okay, sorry, I apologize. The equation got flipped. So the equation was mass equals current times time divided by the Faraday constant times atomic mass of the acquired metal or non-metal under discussion divided by its oxidation number of the metal or non-metal under discussion. So the original equation was M equals Q over F times 8 over Z. So once we flip it for the oxidation number, which is Z, we get IT times atomic mass divided by the mass or whole divided by mass times the Faraday constant, and so when you arrange it becomes 0.8 amps times 965 seconds times 24 grams per mole, whole divided by 0.096 grams times 96,500 coulombs per mole, and you get 2. So the oxidation number was 2, positive 2. It wasn't negative 2, it was positive 2. So we've now gotten this equation, I'm sorry, I flipped it the wrong way, so I apologize. But this is the correct rearrangement of this equation. So this is M equals Q over F times AR over Z. And M equals Q over F times AR over Z. So when you flip it for Z, you get this. And then this is the atomic mass. That's the coulomb over mass times atomic mass times the whole. So coulombs, so IT, atomic mass, whole divided by mass times Faraday constant. You multiply all of this to get to positive. So then you get the valency or the oxidation number. So that's also a very, very useful formula. It can skip you a lot of steps provided you rearrange it correctly. Now, the next question I'd like to pose is for how long I want you to find the time when the current is 0.1 amp and the mass deposited of copper from an electrolytic aqueous solution of copper 2 sulfate is 0.032 grams. So yeah, so the moles. So basically, I want you to find out the time. So I could use this formula again. We've got the mass. I've got the current. I don't have the time. I've got the atomic mass of copper. I've got the Faraday constant, and I've got the oxidation number. So I need this. So what I can do is to rearrange the formula for this, and it'll be and so I rearrange it, and I'll get mass of copper times Faraday constant times the oxidation number of copper 2, which will be 2, so copper sulfate, and the atomic mass was 63.5, and the current passed. So the time taken would be, I'll be using 64 as the atomic mass rather than 63.5. So when I multiply 0.032 grams times Faraday constant, which is 96,500 coulombs per mole, times 2, which is the oxidation number of copper, divided by 0.1 amp, times the 64 grams per mole. So I get 965 seconds, which is round about 16 minutes. So again, this formula is very, very useful for electrolytic solutions. Now this one's for gases, but this one's really very, very useful for mass deposition or finding any of the other missing quantities. So that it's very useful indeed. And this formula will save you a lot of steps, and the examiners know this formula very well because it used to be part of previous books and a lot of Singaporean topic books as well. Topical past paper solutions, but it's now not available in the European books. So again, it's magnificent. It's brilliant formula, and I love it because it saves me a lot of steps. So yeah, so I'm going to do an exam question for you now. The exam question states, aluminium is extracted by electrolysis of solution of alumina, NaL, it's Na3AlF6, cryolite and alumina Al or aluminium oxide, and in a molten cryolite. So this mixture, all of it is called cryolite. And the question is, why do you think it's too expensive to extract aluminium by electrolysis of molten alumina? One of the reasons is high melting point. So when you add impurities, the melting point will be reduced, and so it'll be easier and cheaper to melt and extract as much aluminium as possible. So that's the first reason. Secondly, the yield would be reduced as well, because if you do molar analysis of 2Al over Al2O3 times 100, it's lesser when you've got Na3AlF6 and Al2O3 together. So the percentage recovery would also be slightly higher, but the melting point reduction is a stronger argument. So now you'll have to write equations for the production of aluminium metal and oxygen gas. So at the anode and at the cathode. So at the anode, it'll be oxygen that'll eat into the graphite electrode, and so graphite electrodes need to be replaced from time to time. And at the cathode, it'll be aluminium reaching its elemental metallic form. And so I'll just demonstrate this. So at the anode, it'll be getting released, and at the cathode, it will have to be aluminium ions reduced to reach the elemental state. And so the next question is, the anode requires frequent replacement, as I just said. It was just a reason for this. It's because the oxygen release from the anode continues to eat into the graphite anode. They should have put graphite here. So a current of 100 amps, next question, part D. A current of 100 amps produced 2.7 grams of aluminium in 5 minutes. Calculate the number of coulombs required to deposit 1 mole of aluminium atoms. So it'll be 10 times more, because 2.7 grams is 10 times less than the atomic mass of aluminium. So just by ratio proportionation or Unitarian equimolar proportionation method, I can tell